In this video, we're going to expand upon our knowledge of drawing Bohr-Rutherford and Lewis diagrams of atoms and look at how to draw the same types of diagrams only for ions. Now, before we explain what an ion is, you can take the next few minutes to practice your skills with drawing Bohr-Rutherford and Lewis diagrams of the two elements below, that being sodium and chlorine. If you need a reminder about how to draw either type of diagram, you can go back and watch the second video in this series. But for now, we're going to assume that you know how to draw both Bohr-Rutherford and Lewis diagrams, and we will see each other after you've completed these two diagrams. And thanks to the magic of video editing, we can see what the Bohr-Rutherford and Lewis diagrams of sodium and chlorine look like. So once again, if you have played along and practiced drawing each type of diagram, you can check your answers right now before we continue on to talk about what an ion is and how an ion forms. Now, in order to explain what an ion is, we need to remind ourselves about the significance of the electron shell that is farthest away from the nucleus, which is, of course, what we call the valence shell. So ions form when a specific change occurs to the valence shell of a specific element. Specifically, that's a lot of specifics, an ion occurs when the valence shell becomes full. Now, in the case of both sodium and chlorine, its valence shell is the third shell, which means that in both elements' cases, the maximum number of electrons is 8. And most of the time, this is what we refer to when we say that an element has a full valence shell. It means that there is a full set of 8 electrons, which is why you will also hear the word octet used, octet being the name for a full set of 8. Now, with chlorine, this is actually the easier of the two elements to make this change because chlorine already has 7 valence electrons in its outer shell, which means all that we need to do is we simply need to add 1 electron to its valence shell, which brings chlorine to a total of 8 valence electrons. Now, in addition to filling up the outermost shell to make sure that it has a total of 8, we also designate an ion with a set of square brackets like this to designate the fact that the valence shell is full. Now, the other detail in the structure that needs to be added is something that we call charge, and charge occurs in ions because of the fact that the number of protons and the number of electrons is no longer equal. So chlorine's nucleus has not been altered in any way. It still has 17 protons, which means it has a positive charge of positive 17. However, when chlorine used to have 17 electrons, the fact that we have added 1 electron to chlorine means that it now has a total of 18 electrons, or a negative charge of negative 18. And if we add the positive and negative charge together, we can see that chlorine has a negative 1 charge left over because, again, the number of protons and the number of electrons are no longer equal. Now, if we want to arrive at the number negative 1 in a different way, we can simply look at the change in the number of electrons. So if we add 1 electron to chlorine, this is the same thing as adding a charge of negative 1, meaning we are making the element more negative than it was before. And in integer mathematics, whenever we add a charge of negative 1, this is the same thing as just subtracting 1, and that's how we arrive at chlorine's ion having a charge of negative 1. In fact, we can represent this charge with a change to chlorine's chemical symbol. So to show that chlorine is an ion, ion, we give it a negative sign in the top right-hand corner, or in superscript form like this. And we can also do the same to chlorine's Bohr-Rutherford diagram, giving it a negative sign here. Now, if you want to write 1 minus or -1, that would be equally correct, but normally if you don't write a number, it's implied that the charge is 1. Now, likewise, with the Lewis structure, if we want to make that change, we've added 1 valence electron to chlorine, and therefore we can give it the square brackets as well to designate that it's an ion, and give it a charge of -1 like this. Now, chlorine forms ions the same way that pretty much every other non-metal also forms an ion, by gaining electrons. And as we add electrons, we are adding negative charge, and this means that pretty much all non-metal ions are also going to be negatively charged, and the name that we give to negatively charged ions are what we call anions. Now, if we take a look at a metal like sodium, by contrast, it's a little bit different the way that we find that sodium forms an ion, because if we wanted to add electrons to sodium's valence shell, this would involve adding 7 additional electrons, which seems like a lot considering that we only needed to add 1 in order to get sodium's shell full. So instead, I present you with an alternative. Let's say that sodium gives away its valence electron here. Now, if it gives away this electron, because electron shells are not actually a physical structure, but just space where electrons are located, that means that if this valence electron is not here, that means that the third shell is no longer there anymore, meaning that the outermost shell from sodium, now that the third shell is gone, is actually the second shell, meaning that the second shell is now the new valence shell. And if we look at sodium's new valence shell, we can see 2, 4, 6, 8 valence electrons, and therefore sodium has attained a full valence shell, not by adding electrons, but by losing electrons. And we can see, just based on the numbers of electrons, losing 1 electron, a movement of 1 electron, is much easier to do than adding in 7 electrons, simply because there's less electron movement overall. Now, in terms of the notation, we can label sodium's ion structure the same way as chlorine's, by giving it a pair of square brackets to indicate that it is an ion, and next we need to label the charge. So we can find out the charge either by looking at the number of protons and electrons. So sodium's nucleus still has 11 protons, but because it has lost 1 electron, it only has 10 electrons, and we can see positive 11 minus 10 is equal to a charge of positive 1. If we want to use the change in electron count to find the charge, we can just do some simple integer math. So when we lose 1 electron, that's the same as subtracting a charge of -1, meaning that we are making sodium less negative, and a different way of saying less negative is we are making sodium more positive, because subtracting a negative number is the same thing as adding a number, and therefore we can give sodium's chemical symbol a positive 1 charge in the superscript like this, and add a positive 1 charge to the top right corner of sodium's Bohr-Rutherford diagram. Now, for the Lewis diagram, it's actually quite simple to represent the Lewis diagrams of metal ions, because all that we need to do is we can remove sodium's valence electron. So the Lewis structure is meant to show not only that an element is an ion because it has a full valence shell, but it also shows how that valence shell formed. And because sodium became an ion by losing its valence electron, we don't actually show any valence electrons at all in the Lewis structure, so instead we just give it square brackets and a positive charge in the top right corner, exactly as with the Bohr-Rutherford diagram. So sodium shows that metals form ions fundamentally differently than non-metal ions by losing electrons instead of gaining electrons, and because we are removing negative charge, we are making the metals more positive, and therefore, rather than referring to a sodium ion as an anion, because that's a negative ion, we would call a sodium ion a cation instead. And pretty much every metal and non-metal forms ions in a similar way. So before you move on to the last video in this series, take a look at the periodic table entries of magnesium and oxygen. Draw the Bohr-Rutherford and Lewis diagrams of the element first, and see if you can identify by looking at the valence shell which one is going to lose electrons and which element is going to gain electrons in order to form an ion, and then finish your review by drawing the ion form of the Bohr-Rutherford diagram and the Lewis diagram for each of these two elements. And in the final video in this series, we're going to look at two situations of elements that do not form ions at all.